How's it going, everyone? Welcome to part 2 of our video recording on section 2.5 dealing with limits at infinity. In this second part of the video, I want to go over more examples on how we can use limits at infinity to determine horizontal asymptote, as well as take a look at a more complete problem where we actually find both the horizontal asymptote and the vertical asymptote. So let's go ahead and begin. To evaluate the limit at infinity for any rational function, like the following, the limit as x approaches either positive or negative infinity for p of x over q of x, the key is to divide, or what I would like to consider instead, factor both the numerator and denominator, and this is important, by the highest power of x that occurs in the denominator. So the key for this problem is to take a look at the denominator and identify, hey, which is the x with the highest power, or in other words, which one is the x to the highest degree, and we're going to factor that from everything. So let's take a look at a couple of examples here. Alright, so with example 2, our first limit is the following. We have the limit as x approaches infinity for 3x squared minus x minus 2 all over 5x squared plus 4x plus 1. Okay, so I want you to take a look at the denominator and identify the x with the highest power. So we get to see here that x squared is the x with the highest power in the denominator. Now, we're going to go ahead and factor the x squared from both the numerator and denominator. Okay, so let's take a look. We're going to have here the limit as x approaches infinity. And I'm going to go ahead and factor here the x squared from the top. Alright, so what's left over? We have a 3. Now you might be wondering, it's like, okay, well, how can I factor out an x squared since the second term doesn't have 2 x's and the 2 doesn't have 2 x's there? Well, you might remember that there was a trick to determine, hey, what's left over after I factor something. The key for that is to rewrite the original problem. In this case, since we factored out an x squared, if I go ahead and rewrite the x squared minus x, the original here, and the trick is to divide by what you're factoring here to determine what's left over. There you go, I corrected here. Alright, perfect. So let's see what's left over. Well, in the numerator, we're going to get an x squared times the 3 minus 1 over x minus 2 over x squared. And we get to see this here because, yes, we can simplify. And there we go. That's what's left over in the numerator. But what about the denominator? Well, let's see. If we factor out the x squared and then divide by the nx squared to figure out what's remaining, we're going to be left with, let's see, with an x squared times a 5 plus a 4 over x plus a 1 over x squared. And I'm going to simplify them here so we see what canceled. All right, perfect. Now, once we factor out an x squared from both the numerator and the denominator, well, we get to see here that, okay, well, we can cancel the x squareds. And now we're left with a new expression that we want to take the limit of. We're going to be left with the limit as x approaches infinity for 3 minus 1 over x minus 2 over x squared, and it's all over 5 plus 4 over x plus 1 over x squared. Alright, now we go ahead and evaluate the limit. Now, notice here that a lot of the problems here, or a lot of the terms, are being divided by an x, and as the x gets arbitrarily large, well, 1 over an arbitrarily large number is going to approach 0, 2 over an arbitrarily large number, that's also squared, it's also going to go to 0. And the same thing happens on the denominator. 4 over an arbitrarily large number goes to 0, and 1 over an arbitrarily large number squared also goes to 0. So notice here that a lot of the terms actually went to 0. So we're just left with a 3 over a 5. Okay, now since we got a finite number here, this 3/5, it's actually the horizontal asymptote for this particular expression. So this one, I'll just include it here. The horizontal asymptote for this one is the line y equals to 3/5. Now I would encourage you guys to graph this one either on your graphing calculator or on Desmos, so you do see that indeed you do have a horizontal asymptote. The line equals to 3/5. Okay, now let's go ahead and take a look at another example. And we're going to be using the same approach. Alright, so for this problem, now we have the limit as x approaches a negative infinity for 2x cubed minus 5 all over 3x squared plus x plus 2. Alright, so taking a look at our denominator, we get to see that, okay, the largest, or the x with the power 2, is the x with the largest power. So once more, we're going to go ahead and factor an x squared from the numerator and denominator. So this is going to give us then the limit as x approaches negative infinity of x squared times 2x minus 5 over x squared all over x squared times 3 plus 1 over x plus 2 over x squared. Alright, so just as we did in the previous example, we can we can cancel out the x squareds that we factored, and now we can go ahead and evaluate the limits. Now, beginning with the numerator, I have -5 divided by an arbitrarily large number in the negative direction, so it's going to go to 0 here. And on our denominator, we have 1 over x, which is also going to go to 0, and the 2 over x squared, which is also going to go to 0. Now, we have to be careful for this one here, because compared to the other one, we actually have a term with an x here in the top, in the numerator. Well, if the x is getting arbitrarily large in the negative direction, what we basically have here is the operation of 2 times, now I'm going to put this one here in quotations, 2 times an arbitrarily large negative number, which is going to give us an arbitrarily large negative number. Now this one here, notice that you're actually not getting a finite limit, so for this particular expression has no horizontal asymptote. And this was the key difference between this problem and the previous one. The previous problem actually gave us a finite number, so it does have a horizontal asymptote, but this particular expression does not have a horizontal asymptote. Okay, now let's go ahead and work on another example, but this time around, we don't have a rational expression. Instead, we have the following limit. We have the limit as x approaches infinity for the square root of x squared plus 1 minus x. Now, for this one, if we go ahead and use direct substitution, well, we'd be running into trouble because the first term is the square root of x squared plus 1. Now, because the x is getting arbitrarily large, we're basically having an arbitrarily large number, and then we're subtracting an x, but as the x gets larger and larger, well, we have infinity minus infinity. Now, you may remember from our previous recordings that infinity minus infinity, it's actually an indeterminate form, which we now know that this basically just means more work. Now, since we already encountered problems involving radicals here, you may remember that one of the strategies to see if you can get rid of an indeterminate form is to multiply by the conjugate. Alright, so for this problem, I'm going to go ahead and multiply by its conjugate, and this is going to give us the limit as x approaches infinity for the square root of x squared plus 1 minus x times its conjugate, which is just the square root of x squared plus 1 plus x. But remember, we're essentially multiplying by 1, so that's why we have to multiply both top and bottom. Alright, so what does this simplify to? Well, remember that anytime that you're multiplying conjugates, we can go ahead and take the shortcut and simply multiply the firsts and the lasts. So taking the shortcut, then we're going to get the limit as x approaches infinity for x squared plus 1 minus x squared all over the square root of x squared plus 1 plus x. Now, lucky for us, we can make some simplifications here. I do see that the x squared cancel. Perfect. Now I don't have any variables on the top. Now we can think about what happens as the x gets larger and larger, or arbitrarily large. Well, you get to see here that we basically have a 1 on the top, but on the bottom we have something. You have some variables there. So you have a number that's getting arbitrarily large, which means that our end result here then is going to be 1 over an arbitrarily large number, which is 0. And there we go. Even though we originally had an indeterminate form, as we let the x get larger and larger, after some simplification and manipulation, you see here that the actual limit is 0. Okay, perfect. Now, the last example here, I think it's one of the most interesting ones, because this time around, I am asking you to figure out both the horizontal and the vertical asymptotes for the given function, which is the square root of 2x squared plus 1 all over 3x minus 5. So let's go ahead and take a look at this one here. Alright, so we can go ahead and begin by finding the horizontal asymptotes. Alright, so just as we've been doing, in order to find the horizontal asymptote, we basically need to take the limit at infinity. Okay, so then we have the limit as x approaches infinity for the square root of 2x squared plus 1 all over 3x minus 5. Now, I know that technically speaking, we do need to take the limit as x also approaches negative infinity, but we'll get to it in a second. Okay, so now let's see. It looks like the x with the highest power in the denominator is just an x to the first power. So I'm going to go ahead and factor out an x from both the top and the bottom. Okay, so for this one, I'm going to go ahead and begin with the denominator. Alright, so if I factor out an x, which this time around I'll put here in green. Alright, so I took out an x from the denominator, and what are we left with? Well, this is going to be a 3 minus And now you probably know what to get. It's going to be 5 over x. Perfect. So this one here is our denominator. But what about the numerator though? Because the thing is, on the numerator, you actually don't have an x. No, you don't even have an x squared. What you do have is the square root of a 2x squared plus 1. So this is what I'm going to do on the numerator. It's going to be slightly different. So we're going to have here the square root, but I'm going to go ahead and begin by factoring out an x squared instead. I'm going to get here an x squared times, all right, so what's left over here? Well, we're going to get a 2 plus a 1 over x squared. Okay. In fact, let me give myself a little bit more room. There we go. Now it doesn't look as cramped. Okay, now why did I want to factor out an x squared? Well, now that we've factored out an x squared and we do have a multiplication here, we can actually go ahead and split up the radicals. Now, if we split up the radicals here, we are going to be getting now the limit as x approaches infinity for the square root of x squared times the square root of 2 plus 1 over x squared all over x times 3 minus x over 5. Okay, now this is where we want to be really, really careful. There's a reason why I'm highlighting the square root of an x squared. Now, I know it's very tempting to say that, oh, okay, well, if I have a square root and an x squared, well, we can just cancel the square roots and the squares, and we'd just be left with an x. Now, this one here, it is not entirely true. It is true to some extent. However, I'm going to go ahead and take the opportunity here to give you a very useful hint. Don't forget that whenever we're taking the square root of an x squared, the value is not the x. It is actually the absolute value of x. Now, the reason for that is because, remember, anytime that you're taking a square root, you're taking the principal root, in other words, the positive number. So we have to remember that, hey, the square root of an x squared is actually the absolute value of x. Now, why is this important to know? Well, we saw in class that the absolute value of x is actually the same thing here as the piecewise function, where we have a negative x if x is less than 0, and it behaves as an x whenever x is greater than or equal to 0. So, how is this going to come into play into our problem? Well, right now, since I'm taking the limit as x approaches positive infinity, well then, we're going to be taking values of x that are greater than 0, so it's going to be behaving like the positive value for x. So this problem then is going to give us here the limit as x approaches infinity of x times the square root of 2 plus 1 over x squared all over x times 3 minus 5 over x. And now we can go ahead and cancel our x's here. And now since the limit is since the x values are going to infinity, well then our fractions go to 0 here. And what are we left with? Well, we're now going to be left with the square root of 2 all over 3. And there we go. This is one of the horizontal asymptotes for this particular function. Okay, but well, what if we take the limit as x now approaches negative infinity? If that's the case, then if we take a look at the square root of x squared, but now since the x is approaching the negative infinity, well, now we're picking the function negative x because we're letting values of x be less than 0. So now this time around, we're going to have a negative x times the square root of 2 plus 1 over x squared all over x times 3 minus 5 over x. And once more, we can go ahead and cancel out the x's. And now, if we let the x be arbitrarily large in the negative direction, our fractions here go to 0. And notice we get a very similar result, except that now our answer here is actually a negative square root of 2 all over 3. So this particular function actually had two different horizontal asymptotes. So this problem here, guys, I would say is especially tricky because we need to take into account, again, the fact that the square root of an x squared is actually the same thing as an absolute value of x. So piecewise functions come into play. All right, now I'll give you guys here a couple of pointers. There's a problem that, yeah, you could see in an exam. Okay, now we're not entirely done. We found the horizontal asymptotes. But what about the vertical asymptotes? Well, let's see. Now the good news here is that, remember, vertical asymptotes, they're a little bit simpler. All right, so let's go ahead and find the vertical asymptote. Now remember, to find the vertical asymptote here, we're not taking a look at limits at infinity, but instead, we're looking for infinite limits. So basically what we're doing here is we're looking for a number a, so that when you take the limit as x approaches this number a, you get an infinite limit. All right, so how do we find this number a? Well, it turns out that all that we need to do is set the denominator equal to 0. Okay, so for this problem here, let's see, our denominator was 3x minus 5. All right, so we have 3x minus 5 equals to 0. So that means here that x is equals to 5/3. So what we want to see right now is if our x's get closer and closer to 5/3 in either direction, do we get an infinite limit? Well, let's see. So I'm going to go ahead and take the limit as x approaches 5/3, and the direction doesn't matter as long as you get an infinity, whether it be positive or negative, it is a vertical asymptote. So I don't know, let's go from the left. All right, so we're taking the limit as x approaches 5/3 from the left of our original function, which it was the square root of 2x squared plus 1 all over 3x minus 5. Now, if we go ahead and plug in a 5/3 directly on the numerator, I'm not entirely sure what we're going to get, but I know that it's just going to be some number. We don't have to worry too much about what number we're getting because the problem is in the denominator. Now, for this one here, there's various ways of doing it, but I think you guys would feel a little more comfortable if I actually write down the 5/3 in its decimal form. So let's go to our calculator here. So 5/3 is approximately the same thing as, let's take a look. Let's go for 5/3. All right, so about a 1.6667. Now I decided to round like this. If you want to go a little bit more, that's perfectly fine. All right, now if we picture the number line here, because we want to see what is happening on the denominator as our x values approach the 5/3 or the 1.6667. Now, since we're approaching it from the left, let's see, I'm thinking that maybe we can put in a, let's go here and put in a 1.66666. A lot of sixes here. All right, so once more into the calculator, I'm just going to go, okay, well, if I have 3 times a 1.123455, if I use 5, there we go, minus, well, parentheses, minus 5. Okay, now notice here that we're getting a really small number. So what we basically have here is a number divided by an arbitrarily small negative number. So what does that mean? What are we going to get? Yep, you guessed it. We're going to get a negative infinity. So we are indeed getting an infinity. So the vertical asymptote is at x equals to 5/3. All right, so to finish this section, I'm just going to show you this graph on Desmos so we can verify our work. And there we go. Here we have the original function, the square root of 2x squared plus 1 all over 3x minus 5. And we said that we have a vertical asymptote at x equals to 5/3, and that's what we see here. Here is our vertical asymptote, and this particular function had two horizontal asymptotes. We get to see one over here, the positive square root of 2 over 3. That's what we got when the x was getting arbitrarily large. So yes, our function is approaching that value. Now when x was getting arbitrarily large, but in the negative direction, the function instead is approaching the negative square root of 2 over 3. All right, so this one here, it's a pretty accurate representation. So this is all the stuff that we can do with calculus, guys. Now we have a better way of finding asymptotes. Okay, so this is going to be it for part 2, and hope you guys enjoyed it. See you in class.